Alrighty, good morning, lads and ladies. Welcome back to Pre-Calculus. Today is going to be our second day talking about systems of linear equations, which is a fun moment because we get to introduce some new concepts, some new notation, and we're going to see how to deal with some bigger systems. So we'll see kind of a nice solid method for handling 3x3s, even 4x4s, 5x5s, in theory, larger systems. I won't make you do a lot of the big systems, but I am going to make you learn the methods. So the more fun and rewarding part of the day here is learning what matrices are and seeing how we can use matrices to solve problems like these. So let's get to it. Here. One moment to pour this coffee. Just enough time to make coffee, but not enough time to pour it. Forgive me. All right. So on Monday, we looked at a bunch of 2x2 systems. I introduced you to the concept of row operations, or the individual steps that we use when solving a system by elimination. You can add one row to another, multiply a row by a constant. I will recap those. So this is MAC 1140 section 01, which is pre-calc. And the date today is the 24th of November, 2021. Today we're going to talk about 10.2 and 10.3 on larger systems and matrices. After introducing matrices, there are actually going to be a few sections of the textbook that focus on them. 10.3 focuses on matrices as tools for solving linear systems and as these objects that we can kind of use to replace a linear system. And then later sections, 10.4 and 10.5, will be focused on the algebra of matrices themselves. It turns out you can think of a matrix as like a variable. I don't want to get too far ahead of myself. We'll talk about that when we get there. First, though, let's look at just one or two larger systems, section 10.2. Let me just cook up an example here, because I think we all have some idea of what this will be. We did see one or two linear systems of larger size on Monday. We just didn't do anything with them. Okay. So I think the place your book starts here is not a bad place. Sort of the end game when working or when trying to solve a larger linear system. And remember, we really are only interested in linear systems, is to get the system into a certain form, which your book calls triangular form, using row operations. And I think with your class, I might have left off a row operation. It's not a big deal. And the one I left off is super intuitive. But let me just really quick recap what the row operations are. You can multiply a row by any non-zero constant. And just to be clear about this, that means you can divide a row by a number, right? If I want to divide through a row by 3, that's the same as multiplying through that row by 1/3. So you can multiply through a row by any non-zero constant. Or if you want to think of it the other way, you can say you can multiply or divide through a row by any non-zero constant, because dividing is the same as multiplying by the reciprocal. You can add one row to another. You can add a multiple. Of one row to another row. And the one I left off for you guys the other day, I think, is that you can swap any two rows. So like when you look at your system, the equation that you write first, the equation you write second, you can change the order of those. That doesn't alter the system at all. So these are the row operations. And using these row operations, we will try to take a large system like a 3x3 or 4x4, whatever, and put it into triangular form. So let me show you here a system. We're not going to run through the procedure right now. I'm just going to show you that system sort of in its original form and that same system in triangular form. So let's consider x minus 2y minus z equals 1. This is going to be a 3x3. Negative x plus 3y plus 3z equals 4. And 2x minus 3y plus z equals 10. So here's the original system. And we're going to do row operations to try and turn this thing into, and this is the triangular form for this very system, into something like x minus 2y minus z equals 1. And then the second equation here will be y, all right, 0x plus y plus 2z equals 5. And then 0x plus 0y plus z equals 3. And this is the triangular form. So you start with a system like this. I give you a 3x3, just a regular 3x3 system of linear equations. Doing the same row operations that we were doing yesterday, or sorry, Monday, where you do these things to try and eliminate variables, you get the thing into this form. This form is called triangular because everything below this line, called the main diagonal, is 0. So kind of the only part of the system that's non-zero is this upper triangular portion. So we call this sometimes an upper triangular system, or a system in upper triangular form. Your book just calls it triangular form. Can anybody see an advantage to having your system in this form?
You can perform substitutions easier.
Yeah, sort of. So what does the last equation tell us? That's a valid way to say things. Yeah, a particular kind of substitution that we were using at the very end of these problems is now super easy to do. Back substitution. What does this last equation say right now? I'll label these equation 1, equation 2, equation 3, like we were the other day. Because in triangular form, equation 3 says what?
That z equals 3.
Hell yeah. Right? That last equation, you can now just read off the value of the variable z. So I read that off and I tuck it in my pocket. And now because the equation above, sure, he doesn't just have y's. I can't straight up read off y, but he just has y's and z's. And since I now know z, I can back sub this into equation 2. So that would tell me y plus 2 times 3 equals 5, which means y plus 6 equals 5, which means y equals 5 minus 6 is -1. And finally, with these, equation 1 will tell us that x minus 2 times -1 minus 3 equals 1, which means, well, let's see, x minus 2 times -1, that's x plus 2, minus 3, that's x minus 1 equals 1, which means that x has to be 2. So the solution to the system is the ordered triple. Is the ordered triple to -1, 3. I'll write it x comma y comma z equals 2, -1, comma 3. There we go. So take a second to digest this. We start with a big system, kind of scurry looking. If you were to go about just trying to eliminate one variable at a time, like say I add equation row 1 to row 2, then these x's will go away. And then maybe I add row 1 to row 3 to make the z's go away. And then maybe I try going after the y's here, but if I try to go after the y's here, after getting rid of the x's here, I might bring back this x, something weird might happen. So we got to have a good system for row operations, but you cleverly perform your row operations in order to get into this nice triangular form. Because the third equation then immediately tells you z. Using that, the second equation immediately tells you y. And using both of those, the first equation immediately tells you x. And once you know x, y, and z, you got your solution. A really quick and ordered triple, like 2, -1, 3, that's a point in 3-dimensional space. I will do my best to draw this for you. Drawing 3D pictures is hard, not as hard as drawing 4D pictures, but it's a little joke. Here's your x-axis. Here's your y-axis. Here's your z-axis. So this says you come out 1, 2 along your x-axis. You go out -1 along your y-axis. And then you go up 1, 2, 3 along your z-axis. So here's -1 on the y, +2 on the x. So we're going to this point in the xy plane, which is like the floor. And then we're going to go up 1, 2, 3. So this point right here is your solution to that system. This is the ordered triple 2, -1, 3. The geometry here is not going to be something we worry about as much as we did in the 2x2 case, but I am going to try and show you what's going on geometrically. Geometrically, each of these linear equations represents a plane in 3D space, right? Like a flat sheet. And when you try to solve a 3x3 system, what you're trying to do is find the point where those 3 planes intersect. Rather than attempt to draw those pictures for you, because those are quite tricky to draw, I will show them to you online. First, though, I'd like to take any questions we have on this procedure that we use to solve our 3x3 once it is in triangular form. Here are the kind of individual steps. Everybody super comfy? So if I give you a triangular system, you can solve it, boom, right away. First few homework problems you have from 10.2 are precisely that. Instead of giving you the original system, I just give you instead of giving you this, I just give you this. I just give you the triangular system and say, okay, tell me the solution. All you got to do is back substitute. The third equation will tell you z, back sub to get y, back sub again to get x. The thing we're going to focus on today is row ops. And I'll do one example in that form as a regular system. And I'll do the rest of the examples in the matrix form. So what we want to do here is look at intersection of images. Here we go. That's pretty good. So 3 planes in space. It's possible that all 3 of these planes kind of have different slopes. Slope is a weird word here because it's not the same thing as slope that we normally think of. But this picture, I think, illustrates that case better than the one that I have pulled up here. So if you have 3 planes and they're all oriented differently, then there will be just one point common to all 3 of those planes. If you look at the red plane and the blue plane on their own, they intersect in this dark black line here. And then if you add in the green plane, he intersects that dark black line in the one point here, and that is the solution. They've also highlighted the intersection of the green plane with the blue plane, that is this black line. And they've highlighted the intersection of the green plane with the red plane, that is this black line. Now, in reality, these planes extend forever and ever and ever, amen. But can't draw it like that. So this is the nice case where those three planes, each plane represented by one of these equations, right? This is a plane. This is a plane. This is a plane. Those three planes intersect in a single point because they're all oriented differently. That's not the only possibility, however. Friggin' Cora. Well, no thanks. So what else is possible? Well, what's illustrated, for example, here, if you look at this picture, the pink plane and the blue plane are parallel. Even if they extend forever and ever, they'll never touch. And the green plane chops down through there. So there is no point which is on all three planes. Here, the orange, pink, and blue are all parallel. So again, no point that lies on all three planes. So both of these two would be geometric representations of systems with no solution. What do we think about the bottom right picture here? One solution, no solution, infinitely many solutions. Are there any points that live on all three planes, red, green, and blue? Well, let's see, the red and the green intersect along this line. The red and the blue intersect along this line. And the green and the blue intersect along a line running back there that we can't see. So no, this would also be a no solution case. So no solution, no solution, no solution. Here, red, green, and blue all pointing in different directions. This is a unique solution case. So is this. The one case that's not represented here, this might be it, but it's again hard to see from that particular picture, is something like this, where the three planes intersect along a line. This would be infinitely many solutions. There are infinitely many points that live on all three of those planes. This is kind of the 3D version of having two lines that are the same. There is one more possible case that we're not seeing illustrated here, and that's that all three planes are actually the same, which would again mean infinitely many solutions. So I think that's kind of what they're trying to illustrate here in D. If these actually all sit right on top of each other, like no gaps between them, actually all three the same plane, that would also be infinitely many solutions. It's like here and here, here, infinitely many solutions. Unique solution, no solution, no solution. It's pretty cool stuff. The geometry, again, pictures get a little hard to draw. As the dimensions go up, the pictures certainly become harder to draw by hand. But the procedure for solving these things, thankfully, is the same. So I would like to show you how to do this. And I will do, I think, just one example here before introducing the matrix notation, because frankly, this stuff is unpleasant. And without the matrix notation, there's just so much to write. So if your system is already in triangular form, life is good. Let's take a system that is not in triangular form, like x minus 2y plus 3z equals 1, x plus 2y minus z equals 13, and 3x plus 2y minus 5z equals 3. We're going to solve this by using row operations to put it into triangular form. I'm going to do this in a certain way. And after demonstrating it, I will kind of show you or walk you through the individual steps and tell you why we always do it in this way. You focus one column at a time. This x is allowed to stay here, but these two got to go, right? Because I need everything down here. I need these and this to be a 0. Remember, I want everything below this main diagonal to be 0. That's my upper triangular form. So I need this x to be a 0. I need this 3x to be a 0, and I need this 2y to be a 0. And I don't want to mess one of the things that I've already done up when I go to work with something else. So what you do is first you clear out everything beneath that top left entry. Then you go after this guy. So my first row operation, which is designed to kill the x in this position, I'm going to be changing row 2. So my new row 2 is going to be my old row 2 minus my old row 1. In other words, I'm going to multiply row 1 by -1 and add it to row 2. This is that third type of row operation where you add a multiple of one row to another row. The trick here is that only row 2 is going to change. I'm using row 1 as a tool to modify row 2, but I'm not changing row 1 and I'm not changing row 3. And this takes a second for people to get their head wrapped around because it says I'm going to multiply row 1 by -1. But that's not the row op I'm doing. I'm multiplying row 1 by -1 and adding that to row 2. That's a single row operation that leaves rows 1 and 3 unchanged. It only changes row 2. So first I'm going to copy down the rows that don't change. Row 3, 3x plus 2y minus 5z equals 3. He is not changing. Row 1, I am not changing. X minus 2y plus 3z equals 1. Row 2 is the row that's changing. Make faces at you. So I'm going to multiply this by -1 and add it to this. -1 times x plus x is 0x. -1 times 2y, sorry, -1 times -2y is positive 2y, plus 2y is plus 4y. -1 times 3z plus -z is -4z. And don't forget to do the right-hand side. -1 times 1 is -1 plus 13 is positive 12. This is what we get when we multiply row 1 by -1 and add it to row 2. In other words, subtract row 1 from row 2. Yeah, Shauna?
I'm sorry, that was my cat.
No worries. All right. So rows 1 and 3 stay the same. I am using row 1 as a tool to modify row 2. And that gets me a 0 in this position. My next step is to get a 0 in this position. And again, I'm going to use row 1 as the tool. So what I'm going to do is I'm changing row 3. And row 3 is going to be my old row 3 minus 3 copies of old row 1. In other words, I'm multiplying row 1 by -3 and adding it to row 3. So row 1 stays the same. Row 2 stays the same in this step, 0x plus 4y minus 4z equals 12. Row 3 now is going to change. So -3 times this plus this is 0x. -3 times -2y is positive 6y. 6y plus 2y is 8y. -3 times 3z is -9z. -9z plus -5z is -14z. -3 times 1 is -3 plus 3 is 0. And you see the importance of doing kind of one thing at a time, right? One row up at a time, and also the importance of this notation, because God forbid you make a mistake. I can't tell you how important it is to be just very, very careful as you do these, right? Each row operation is going to involve like 3 little arithmetic things or 3 little algebra things. And it's very possible to make a tiny little mistake in one of those things, and that will destroy the whole rest of the problem. So you need to be super scrupulous. You want to check your work at each step, and you want to write down the row operation that you're doing so that if you make a mistake, you can come back and be like, okay, where did I go wrong? What did I do? And that way you don't have to start the whole thing over again. You just go back to the step where you made a mistake and fix it from there. So what we've done is we've used row 1 as a tool to make both of the entries here 0. All right, that's what we have now. I've got x in the top right, top left, and then zeros below. I'm almost into that triangular form. The only thing I need to do to get my triangular form now is this. There are some other things we can do, and I'll show you some nice ways to clean up the system at the end. Does anybody see a row operation I can do that will allow me to get rid of this guy?
I actually have just a really quick question.
Yeah.
So when you take in this last one, like equation 1, and you multiply it times 3, you leave the original in the system. You don't leave like the after it's multiplied by 3 in there.
Right. So, and this is, I know it's a little bit weird, right? But think of it as a single step where I'm going to multiply this by -3 and add it to this. Really, multiply this by -3 and add it to this. I'm picking up the hammer, whacking the nail, but then I'm setting the hammer back down. So like this is my hammer. I'm not going to leave it on the nail. I'm just going to pick it up, use it to whack this thing, and then set it back down.
Thank you.
It feels a little bit weird. It always takes a second, and that's okay. But if we could do these in separate steps. Let me say it like this. If we're more comfortable with the individual row ops that we talked about on Monday, you could say, I'm going to multiply this row by -3, one step. Second step, I'm going to add that new modified row 1 to row 3. That will get me this version of row 3, but would have this multiplied by -3. And so then for a third step, I could say, okay, now I'm going to multiply row 1 by -1/3 to return it back to this form. But doing that is much more complicated. You end up writing out a lot more steps. So I prefer the way of thinking that I described a second ago. I'm going to use this as a tool to modify this. I'm not actually changing this. I'm just picking this up and using it to whack this thing to death. All right. So I've got the zeros here that I wanted. The only other thing I need is a 0 here. Can anybody suggest a row operation to make this 0? I see two possible options. I'm just curious what you guys see.
Multiply equation 2 by -2.
Yeah, if I multiply this by -2 and add it to this, -2 times 4y is -8y, that'll kill this, right? Does anybody see the other row operation that would give us a 0 here? The one Shauna identified is the one we're going to do, for the record. But does anybody see another row operation that would get rid of the 8y?
Can we use the first equation and multiply it by 4?
Yeah, if I multiply this by 4 and add it to this, that will also get rid of the 8y. Why don't I want to do that? So I appreciate you saying that, Joyce. I'm trying to pull it out of you guys. The first one is the one we're going to do, and there's a good reason, but I want us to be aware of both and see why the first one is the one that we want to do. So your answer was perfect. And we go a little bit deeper and say why we should use this as our hammer instead of this when it comes to attacking this thing.
Is it because of the zeros in the front?
Yeah, I want to keep these as 0. If I multiply row 1 by 4 and add that to row 3, I will get a 0 here, which I want, but 4x plus 0x is no longer 0x. This would turn into a 4x. I would have undone this good work that we did here. So the nice thing about clearing out the stuff in column 1 first is that when you go after the stuff in column 2, you can use this equation, which already has a 0 here and won't mess up the 0 here when you attack this position. That's the idea. It's very clever and it's not obvious. And that's why I say we have a specific order that we do these things in, because if you just kind of run around trying to eliminate stuff, it's very easy that going after the y's brings back the x's. And that's not what we want. We want to get into triangular form as quickly as possible. So my next row up here is going to be row 3 is equal to old row 3 minus 2 copies of old row 2. I'm going to multiply this by -2 and add it to this. The only row that changes here is row 3. Rows 1 and 2 don't change. All right. -2 times this plus this is still 0x. That's the good news. -2 times this plus this is 0y. More good news. -2 times this is positive 8z. 8z plus -14z is -6z. And we have to be careful over here as well. -2 times this is -24 plus this. 24. Now we are in triangular form. Here's my main diagonal. Everything beneath that is 0. So we've solved the system. We just have to back substitute. Now there are two other little row ups we could do to kind of clean things up here if we wanted. And I'll do them both in a single step. Row 2, everything is divisible by 4. I've got a 4y, negative 4z, and 12. So if I want to, I can clean up row 2 by dividing everything by 4. In other words, I'm going to multiply through row 2 by 1/4. Also, in row 3, everything is divisible by 6, even negative 6. So I'll say my new row 3 is negative 1/6 old row 3. So I'm going to divide through row 2 by 4. I'm going to divide through row 3 by negative 6. And that will, I don't know, I'm already in triangular form, but that will get me this maximally clean triangular form, which is easier to back sub into. So 4y divided by 4 is y, negative 4z divided by 4 is negative z, 12 divided by 4 is 3. And down here, negative 6z divided by negative 6 is just plus z. Negative 24 divided by negative 6 is positive 4. So these are my row operations. And now this is a very nice triangular form. Not only is everything beneath this main diagonal 0, which is what I wanted, but also the entries on the main diagonal all have coefficient 1. That's another really nice thing. So now we can solve, we can write down the solution. It's up here. Now we see from equation 3 that z is equal to 4. Back subbing into equation 2. We get y minus 4 equals 3, which means y is 7. Both of these into 1. Gives us x minus 2 times 7 plus 3 times 4 equals 1, which means x, let's see, minus 14 plus 12 is minus 2 plus 1. So x has to be 1 plus 2, which is 3. Plus my solution is 3, 7, 4. That's it. And that's how you solve 3 by 3s. It's also how you solve 4 by 4s, 5 by 5s, 10 by 10s. Same shit. I want to do a couple things now. I want to kind of put in words the procedure that we used here. And I want to introduce the matrix notation because it'll save us an awful lot of writing. You can, anytime you solve a 3 by 3, you can write everything out like this. But what matrices do, they just allow you to stop writing the curly bracket, stop writing the x's, the y's, the z's, and the equal signs. You just write the numbers, right? Like this first row here, I could think of this as 1, -2, 3, 1. where I know that the first number is the coefficient of x, the second is the coefficient of y, the third is the coefficient of z, and the last is the right-hand side. I can just let their position in the array tell me what variable they're attached to. The other thing is to describe Gauss-Jordan elimination. Yeah, let's do it. Maybe matrix notation first. I'm going to define what a matrix is for you. An M by N matrix is a rectangular array of numbers with M rows and N columns. That's it. We usually use capital letters to denote a matrix. And there's kind of two notations. I like the parentheses notation. You can also use a big square bracket. And then the entries here are indexed with a subscript. So A11, A12, A13, all the way out to A1n. This is the first row. The second row would be A21, A22, A23, all the way up to A2n. And there are m rows, so the last row here would be AM1, AM2, AM3, all the way out to AMN. This is a matrix. The entries here we call Aij. So this first number tells you what row you're in, and the second number here tells you what column you're in. So for example, A23 is in row 2 and column 3. Aij is the entry, which remember entries, these are numbers, in row I and column J. M by N we call the dimension or size of the matrix. That first number is the same thing as the dimension or size of a system. The first number is the number of rows or equations if you're talking about a system. The second number is the number of columns or variables if you're talking about a system. It is a fact we can find a matrix associated with any linear system the entries of that matrix are the coefficients just the numbers from the system. So what I'm going to do now is write down a system and then show you the associated matrix. Really, there's two matrices associated with any system. One of them includes the right-hand side, and that's called the augmented coefficient matrix. One of them doesn't include the right-hand side, and that's just called the regular coefficient matrix. We will work with the augmented coefficient matrix in the next two sections. So start with the system. X minus 2y. Actually, hang on. Let me see. That's the one we just did. How about x plus 2y minus 2z equals 1. 2x plus 2y minus z equals 6. And 3x plus 4y minus 3z equals 5. And I can say that this is basically the same thing as this equal sign where the top is shaky and the bottom isn't, is the symbol for isomorphism. This has the associated matrix 1, 2, -2, 1. Just the numbers from the first row. Second row would be 2, 2, -1, 6. Just the numbers from the second row. And the third row in my matrix would be 3, 4, -3, 5. There it is. To remind myself that these numbers are on the right-hand side of the equal sign, that the equal sign lives right there, I like to put a little vertical line here. So this part, this little 3x3 submatrix is called the coefficient matrix. It is the rectangular array of coefficients from this system. And the whole thing is called the augmented coefficient matrix. So it has been augmented or added onto with the right-hand side. So this 3x3 submatrix, this is just called the coefficient matrix for the system. And the whole thing is called the augmented coefficient matrix for the system. The magic of these things is that this carries all the same information as this system, but there's way less to write. I'm not writing the equal signs. I'm not writing any of the variables. I know that the numbers over here are the numbers attached to Z. I know that the numbers here are the numbers attached to Y. And I know that the numbers here are the numbers attached to X. I just let their position on the page tell me what they mean. So if I want to know what does the 3, 3 position here tell me, this tells me that there is a negative 3Z in the third equation. If I want to know what does the 1, 2 position here tell me, this tells me that there's a plus 2y in the first equation. If I want to know what does the 2, 4 position tell me, it tells me that the right-hand side of the second equation is 6. So I can give you a system and ask you to write down the augmented coefficient matrix. Or I could give you an augmented coefficient matrix and ask you to write down the system. You can do to matrices all the same things you can do to systems. Namely those row operations. We can perform the same row operations on matrices that we used on systems. Like I can add row 1 to row 2, or I can add 3 times row 1 to row 3. So what we're going to do, given a large system, is write down its augmented coefficient matrix. Then we will turn the augmented coefficient matrix into upper triangular form by making all of the entries here 0. Then we will go back from the matrix to a system and solve that new system, which will be an upper triangular system, by back substitution. For now, just think of the matrix as a way of encoding the system. It's a way of writing less, saving you some ink and paper. Later, I will show you that there is a whole algebra of these matrices. You can treat these objects as algebraic objects in their own right, and you can solve a linear system by doing some matrix algebra, which will be fun. This is a great way to scare the shit out of your friend taking college algebra. The notation just looks pretty cool, right? And it looks weird. Doesn't look like any of the math you see in high school usually. What I would like to do for you now is to solve this system, or attempt to solve this system, by row reducing. That's the term, row reducing this matrix. So let's run through that same procedure that we just used. Let's see what we get here. Okay. So now let's perform row ops. Excuse me, on this matrix to put it into triangular form. Oh, you see, we're just, it's the same shit. We're just not writing the variables anymore. That's all. So what I need to do is make these zeros, and then I make this a 0, right? How do I make these zeros? Well, let's see. I can take row 1, multiply it by -2, and then add that to row 2. So my new row 2 is going to be my old row 2 minus 2 copies of my old row 1. And that will get me a new matrix where row 1 is still 1, 2, -2, 1. Row 3, copy down the stuff that doesn't change first. Row 3 is still 3, 4, -3, 5. But now row 2, I multiply this by -2 and add it to this. That's 0. Multiply this by -2 and add it to this. Oh, that's interesting. -2 times this is -4 plus this is -2. Multiply this by -2. That's +4 and add it to this. That's +3. Multiply this by -2 and add it to this. So that's -2 plus 6 is +4. And I do like to keep this bar in here, this little separation bar. Right. So I multiplied everything up here by -2 and added it to this. -2 times this is -2 plus this is 0. -2 times this is -4 plus this is -2. -2 times this is +4 plus this is +3. And -2 times this is -2 plus this is +4. And 1 and 3 didn't change. Is everybody good on this first row up? Any questions about what we've done here? And at any stage, I could go back and rewrite this as a system, right? At any stage, I could go back and say this is x plus 2y minus 2z equals 1, 0x minus 2y plus 3z equals 4, 3x plus 4y minus 3z equals 5. At any stage, I could go back to a system. But I'm going to work with it as a matrix until I get it into that nice form. Then I'll go back to putting it as a system. Next, I want to kill this 3. Again, row 1 is my hammer. I'm going to use this row to smash this 3. So I'm changing row 3. It'll be my old row 3 minus 3 copies of row 1. First, copy down the rows that don't change. 1, 2, -2, 1, 0, -2, 3, 4. -3 times this plus this is 0. -3 times this is -6 plus this is -2. -3 times this is +6. +6 plus -3 is +3. -3 times this is -3 plus this. What is it? -3 times this is -3 plus 5 is 2. There's my second row. And you see it's just cleaner. Now something kind of neat has happened to the coefficients in here. This and this are the same. I've got my zeros here. I want a 0 here next. So I'm going to be modifying row 3. Row 3 will be -1 times row 2. So it's old row 3 minus old row 2. Multiply this by -1 and add it to this. Rows 1 and 2 don't change. 1, 2, -2, 1, 0, -2, 3, 4. -1 times this plus this is still 0. -1 times this is 2 plus -2 is 0 by design. -1 times this is -3 plus 3. Ooh, we also killed that in the same move. -1 times this is -4 plus this is -2. So there's the whole procedure for putting this matrix into triangular form. And I got the zeros where I wanted them, here, here, and here. I also got a 0 here. So let's now put this back into the form of a system. X plus 2y minus 2z equals 1. Right? 1, 2, -2, 1. That's 1x plus 2y minus 2z equals 1. 0x minus 2y. I won't write the zeros. Plus 3z equals 4. Oh, maybe I will. Yeah, why not? Sure, that's what we've been doing. And then the last row says 0x plus 0y plus 0z equals -2. All right. What do you guys think is going on with this system? This system down here.
Is there no solution for the entire thing?
Very good. Very good. Exactly. So first, before I get into that, any questions on the matrix notation, row operations, stuff we did here? Questions on any of this? Okay. Then what about that comment? So here we get the feeling that there's no solution. Why? You're 100% correct, Sean. I'll just tell me a little bit what you're thinking. It's the same sort of thing we saw on Monday, right? The problem is this equation. Equation 3 now says 0x plus 0y plus 0z equals -2. In other words, 0 equals -2, which is a contradiction. Right? A lie. A dirty lie. It's just not true. 0 is not equal to -2. Which means that this system can't possibly have a solution. We call it an inconsistent system. And once you get really comfy with the matrix notation, you'll realize that as soon as you get something like this, where all of these are zeros, but this is not zero, that's exactly what that says. If you ever have a row of all zeros on the left and non-zero on the right, that means that 0x plus 0y plus 0z equals some non-zero number. That's impossible. That's a contradiction. So we could, if we were being very astute, say from here that the system has no solution without even rewriting it like this. But that's it, we're done. The system has no solution. I want to show you one more.
Wait, I'm sorry. Does that, so the whole three equations have no solution because one doesn't have a solution?
Well, remember what a solution, so the system, it's not the case. No, each one of these equations, except the last one here, on their own would have many solutions. But the system has no solution. Remember what a solution to the system is. It's an ordered triple. It's a value for x, y, and z that make all three equations true at the same time. So what we mean when we say that the system has no solution is that there are no numbers x, y, and z that we can plug in here that will make all three equations true at the same time. So for example, this first equation, if I plug in 1 for x and 0 for both y and z, this first equation is true. So 1, 0, 0 would be a solution to this first equation. But that does not solve the other two equations. So it's not that none of the equations have a solution, it's that the system as a whole has no solution, meaning so what this means is there, i.e., there are no numbers x, y, z which solve all three equations at once. So remember what a solution to a system of equations is. It's a value for each of the variables that satisfies all equations simultaneously. Each one of those original equations has infinitely many solutions, and those are the points that live on the plane. But what this means is that there's no single point that lives on all three planes. What's actually going on with this, the geometry of this particular system, is that the third plane is the sum of the other two. So if you add equations 1 and 2, you get equation 3. And that means that the first two planes are the same plane. No, wait, what does that mean? That means, I'm not too sure what the geometry there would be. I think for just a moment. The first two planes intersect in a line, and the third plane is disjoint from that line. That's what this would mean. But from our perspective, we've done the normal row operations. Imagine you just worked entirely with the system notation, never doing anything with matrices. You just work with the system notation and you arrive at something like this. That third equation no longer has any solutions. Right? In the modified version of this system that we get by doing our row operations, that third equation has no solutions, which means that the system as a whole has no solution. In other words, there are no numbers that you can plug in that make all three equations true at the same time. If you want to hang around for a second after class, I can try to show you the geometry. I can try to graph this system for you in some software. But we do need to get through one more example here. I know that we're right at 9:15, but I'm going to ask you to hang out because I do want to show you one more here before I let you go. 2x plus y plus, so this should be a 4z. 4z equals 2. And then 2x plus 4y minus 2z equals 8. And this is a plus, sorry. X plus y plus c negative 2. 2x plus y plus 4z equals 2. 2x plus 4y minus 2z equals 8. Okay. Yeah, so when I originally wrote down row 2, this needs to be a plus and a 4z. All right. We're going to begin by putting this into the matrix form. 1, -1, 5, -2. 2, 1, 4, 2. And 2, 4, -2, 8. There's my augmented coefficient matrix for this system. Then I'm going to run the normal row operations to make this stuff 0, make this 0. So my new row 2 is going to be my old row 2 minus 2 copies of my old row 1. I want to multiply this by -2 and add it to this. Row 1 doesn't change. Row 3 doesn't change. Row 2, -2 times this plus this is 0. -2 times this is 2 plus this is 3. -2 times this is -10 plus 4 is -6. -2 times this is +4 plus 2 is +6. So there's my first row. I want to do the same thing to row 3. I want to kill this too. So my new row 3 will be my old row 3 minus 2 copies of my old row 1. In other words, I'm multiplying row 1 by -2, adding it to row 3. Rows 1 and 2 don't change. -2 times this plus this is 0. -2 times this is 2 plus this is 6. -2 times this is -10 plus -2 is -12. -2 times this is 4 plus this is +12. So now I've got my zeros in the first column down here. I want everything beneath this main diagonal to be 0, so I need to kill the 6. And to kill the 6, I will multiply row 2 by -2 and add it to row 3. So my new row 3 is my old row 3 minus 2 copies of my old row 2. Rows 1 and 2 don't change. Zero times -2 plus 0 is still 0. 3 times -2 is -6 plus 6 is 0. -6 times -2 is +12 plus 12 is 0. And 6 times -2 is -12 plus 12 is 0. So again, I have a row of all zeros over here. And if this was not 0, then I would know there's no solution. This is a lot like when we had 0x plus 0y equals 0 on Monday. Right? In fact, right now what equation 3 says, let me go ahead and put this back into the form of a system. I've got 1x minus 1y plus 5z equals -2 for my first row. 0x plus 3y minus 6z equals 6 in my second row. And 0x plus 0y plus 0z equals 0 in my third row. This guy is a tautology. 0 equals 0. And what does that mean? What does that tell us about the system? Well, just like on Monday, this means that the system has infinitely many solutions. And just like on Monday, I need to characterize those infinitely many solutions. I need to describe what they are. It's not true that any ordered triple solves this system. What is true is if we let z be just t, then I can solve for the other variables in terms of t. Then equation 2 becomes 3y minus 6t equals 6. You can divide through over here by 3. Let me just do the normal thing. So say that means 3y is equal to 6 plus 6t. And then dividing by 3, that means y would be 2 plus 2t. Finally, equation 1 tells us, so I'm going to plug in t for z and 2 plus 2t for y, x minus 2 plus 2t plus 5t equals -2, which means x, let's see, I've got -2 minus 2t plus 5t. That's x minus 2 and then plus 3t equals -2. Add the 2 over, x plus 3t equals 0. So x is -3t. So the solution here is any ordered triple of the form x, which is -3t, comma, y, which is 2 plus 2t, comma, z, which is just t. So unique solution, no solution, infinitely many solutions. Just like with 2x2s, 3x3s can yield all of these possibilities. And the way we handle everything is the same as we handle them with 2x2s. The nice thing here is that we have an excuse to start working with matrices. The truth is you can work through all of the current homework set without using matrices if you want to write all this system stuff in every single step. But I think you agree, comparing the amount of work and writing that it is just putting things in the matrix to the amount of work and writing you have from that very first example where we worked in the system notation, the matrices are nicer. And more importantly, as we move into 10.4 and 10.5, we'll be working exclusively with matrices. Those sections you will need to use matrices. So I introduce them now and encourage you to start getting comfy with them because they're really the way to go. I have to get running. I do have another class that starts in 3 minutes here. I've got an office hour today from 1 to 2 p.m. if you want to talk about anything. Otherwise, you can always send me a Canvas message or an email or Discord. You know the drill at this point. That's it from me. Please work on this homework. Please try to enjoy some of these matrix things because these are really beautiful objects in mathematics and they're a lot of fun to play with once you get comfy with them. Like I said, if there's anything you want to talk about, struggling with, anything like that, please reach out. Otherwise, I will see you guys after the holiday. Take care.